Hello friends, in today's topic we will try to understand the characteristics of digital ICs. The performance and the quality of digital ICs depends on its characteristics, and there are some characteristics which we have to discuss all about. Then these characteristics are very useful in comparing which type of logic family is more useful to construct the logic gates or logic circuits. Starting with the current and voltage parameter, we will move to noise margin, fan in, fan out, power dissipation, figure of merit, propagation delay time, and operating temperatures. These are some important characteristics of digital ICs regarding the logic gates. Starting with the current and voltage parameters. Before we start to understand the current and voltage parameter, let's have a look at this diagram. In this diagram, you can see there is a OR gate which is shown here, and on the left hand side there is an input, and on the right hand side there is output. The Boolean equation for OR gate is A plus B, but when these gates are used, the logic, the binary numbers or binary logic, it is given in the form of voltages or in the form of current. On the left hand side, you can see there are certain voltage ranges and certain current ranges. On the right hand side, it is also mentioned some voltage and current ranges. At the input side, which voltage is considered as logic 1 and which voltage is considered as logic 0. These voltage ranges are, the voltage ranges and current ranges shown here are not the exact. We have at randomly taken some voltage ranges to clear the idea about the voltage and current parameters. Let's have a look on the left hand side. There is a voltage for logic 0, and the voltage range for logic 0, it is given from 0.2 volt to 0.4 volt. Similarly, for logic 1, the voltage level at the input is 3 volt to 5 volt. So these are the voltage level that can be understood by the gate as logic 0 and logic 1. Along with this voltage ranges, which current or which value of current will be considered as logic 0 and which value of current will be considered logic 1, that ranges are also shown here. The current ranges for logic 0 is 2 milliampere to 4 milliampere. So the current in between this range will be considered by the gate as logic 0. Similarly, for logic 1, the current ranges are 30 milliampere to 50 milliampere. That means the current ranges in this value will be considered as logic 1 by the gate. Similarly, on the right hand side, you can see the voltage ranges for logic 0 as 0.4 volt to 0.8 volt, and for logic 1, 3.5 volt to 5 volt on the right hand side for output side. Similarly, the current ranges for logic 0 at the output is 4 milliampere to 8 milliampere, and for logic 1 it is 35 milliampere to 50 milliampere. Now these values are only for example, so these are not the exact value. Now to understand, to remember the current and voltage parameter definitions, these examples are taken. Now back to current and voltage parameters, how these are classified and how they are defined. So let us see. Or voltage parameter is the high level input voltage, that is VIH. Now the definition of this parameter is this is the minimum input voltage which is recognized by the gate as logic 1. This is the definition of high level input voltage. From the diagram you can see we have assigned a voltage range from 0.2 volt to 0.4 volt as the input voltage for logic 0. Now from the definition, this is minimum input voltage which is recognized by a gate as 1. Now back to the definitions of current and voltage parameter. The first voltage parameter is high level input voltage, that is VIH. In the diagram you can see logic 1, it is represented by the voltage range as 3 volt to 5 volt at the input side. So high level input voltage means at the input which voltage is considered as logic 1, that is the definition of high level input voltage VIH. It defines that it is the minimum input voltage which is recognized by a gate as logic 1. See what it is said, it is minimum input voltage which is recognized by the gate as logic 1. So from the range 3 volt to 5 volt, the minimum voltage is 3 volt. So 3 volt is the high level input voltage and it is denoted by VIH, because if the voltage is 2.9, this voltage will be considered as logic 0 by the gate at the input. But the voltage which is more than 3 volt, it may be 4 volt, it may be 5 volt, it may be 6 volt and so on. So the voltage which is greater than 3 volt, it is considered as logic 1 by the gate at the input. So this is the high level input voltage VIH. Now the second definition is low level input voltage VIL. In the voltage range 0.2 volt to 0.4 volt, this was the range for the gate which is recognized by the gate as logic 0. So it is defined that this is the maximum input voltage which can be recognized by the gate as logic 0. 0.2 volt and 0.4 volt. So 0.4 volt is the maximum voltage. So this voltage is the low level input voltage. Why? Because if the voltage is 0.4 volt, it will be considered as logic 0, but the voltage is more than 0.4 volt, suppose for example it is 0.5 volt, it will be considered as logic 1 by the gate at the input. So the maximum voltage is 0.4 volt, so that is why this voltage is taken as VIL, that is low level input voltage VIL. The third definition is high level output voltage. It is defined that this is the minimum voltage available at the output corresponding to logic 1 and it is denoted by VOH, that means at the output high voltage level. So in the diagram you can see the 3.5 volt to 5 volt, this was the voltage level for logic 1 at the output. So the definition is this is minimum voltage available at the output corresponding to logic 1. So 3.5 volt to 5 volt. So minimum voltage is 3.5 volt. So the voltage below 3.5 volt is will be considered as logic 0 and 3.5 volt it will be considered as logic 1. If the voltage is greater than 3.5 volt, no problem, it will be considered as logic 1. So 3.5 volt is the VOH in this case. The fourth definition is low level output voltage. So again it is defined as this is the maximum voltage available at the output corresponding to logic 0. What is said? Maximum voltage available at the output. So maximum voltage, you can see the voltage ranges, it is 0.4 volt to 0.8 volt and 0.8 volt will be the output low level voltage. Why 0.8? Because from 0.4 to 0.8 the ranges are this, the logic level will be considered as logic 0. If the voltage is more than 0.8, if it is 0.9, that will be considered as logic 1. So that is why the maximum range is 0.8. So up to 0.8 it will be considered as logic 0 at the output. Similarly, if you see the voltage levels, corresponding current will be there. Those currents are also defined and it will have the current parameters too. First of all, let us see how high level input current, that is IIH. At the high level, the current ranges at the inputs are 30 milliampere to 50 milliampere. So IIH, that is high level input current, it is defined as this is the minimum current which must be supplied by the driving source corresponding to logic 1 level voltage. If these gates are connected to any other source to connect the binary levels, that source should have this much current, then only the gate will consider it as logic 1. The ranges are 30 milliampere to 50 milliampere. From this, the minimum current is 30 milliampere. So IIH is 30 milliampere. So this much current must be supplied by the source. and that will be recognized by the gate as logic 1. The next is low level input current, that is IIL. In the same way, 2 milliampere to 4 milliampere, this is the range for logic 0. So minimum current is 2 milliampere. So this much current must be supplied by the source to the gate, and that will be considered as logic 0 by the gate if the current ranges are 2 milliampere to 4 milliampere. It means that the minimum value of current should be 2 milliampere. If the current is more than 4 milliampere, it will be considered as logic high. So the ranges are 2 milliampere to 4 milliampere. Then high level output current, that is IOH. High level output current, from the right hand side you can see for logic 0 it is 4 milliampere to 8 milliampere is the range for logic 0, and 35 milliampere to 50 milliampere is the current range for logic 1. The maximum current as the gate can sink in logic 1 level is the high level output current. So for high level, the current ranges are 35 milliampere to 50 milliampere. So here the maximum current should be taken. That means 50 milliampere. This will be the current. That current, if it is supplied by the output of the gate, that will be considered as logic 1. In the similar way, 4 milliampere to 8 milliampere is the range for logic 0. So 8 milliampere is the maximum current, and this will be current for low level output current. So this was the high level and input and output voltage parameters. Two more parameters are defined here: high level supply current and low level supply current. High level supply current is the supply current when the output of the gate is logic 1. That means when this logic circuit or logic gate it is connected to the power supply, the current will be supplied by the power supply, and if the output of this gate is logic 1, the value of current supplied by the power supply will be called as high level supply current, that is ICC for logic 1. If the output of logic gate is 0, then that current from the power supply sinking, then that current it is called as low level power supply current, that is ICC for logic 0. So this was the current and voltage parameters. Now let us move to another definition, noise margin. When these digital circuits are connected to one another, they should have to connect their inputs and outputs with the use of cables or wires. Now if these wires are passing through a magnetic field or through an electric field, they may introduce unwanted voltage inside the wires which are carrying the digital data, and this unwanted voltage is called as noise. On the connecting wires between the logic circuit, this will introduce the noise, and the voltage at the input of logic circuit may drop below the VIH or may rise above the VIL, and the digital circuit may produce the undesired operation for logic circuit. Now this logic gates should be able to withstand such type of fluctuations in the voltage levels of digital data, and the ability of these logic circuits to tolerate these signals is called as its noise immunity. And the noise margin, it is the qualitative measure for noise immunity. In the diagram you can see there is a low level margin shown here and high level margin. The difference between VOH and VIH, that is high level output voltage and high level input voltage, these values of voltage, if the difference is taken, that will define the noise margin for logic 1. Similarly, low level input voltage and low level output voltage, if you consider these voltage levels and if their difference is taken, that will define the noise margin for logic 0. So noise margin is nothing but the qualitative measure of noise immunity of a logic gate, and noise immunity means the ability of logic circuit to tolerate the noise. So this was about noise margin. The third definition for parameters or characteristics of logic gates is propagation delay, or it may be called as the speed of operation. In the diagram you can see there are two waves shown here, one wave for input voltage and one wave for output voltage. In the diagram we have taken an example for NOT gate, and if these voltage levels are taken in the milliseconds, then this type of voltage will be shown. At the input you can see the input is remaining 0 for some while, and then after that the voltage level is changed. That means the input is right now low, and if it is changed to high level, it will take some time to change the input state or voltage level from low to high. This will take some time from 0 to high, so that is why the line is inclined. And suppose the voltage is now remain at high for some while, and then if it is again changed the state from high to low, again it will take some time, so the again inclination is shown there. So this is the input wave. Suppose we have taken a NOT gate and this type of voltage is given to the NOT gate, there will be changes in the output as per the input voltage. From the second below wave, you can see the output is remaining high for some while when the input was 0. So in the NOT gate the complements are obtained. So when the input is low, output is high shown here. When input is remaining 0, output will be 1. Now if input is changed from 0 to high, that will also take some time to reach at the output, and so output will change after some while. It will not be done at the same time. So the output will take some time when the inputs are changed. So output will also take to change its state. So when input is changed from 0 to 1, the output will change from 1 to 0. So that will also take some time. After this, the input is remaining high for some while. The output also remains 0 for some while. Then after that, if input state is again changed from high to low, the output will not suddenly change. It will take some time and it will change from low to high again. So this will also take some time. Now you can see, if you compare the voltage levels of input and output, the input voltage and output voltage levels, they are differentiated with the 50% margin, and it is shown by a dotted line at the input and at the output also. So when input has been changed from low to high, output is changing from high to low because it is NOT gate. So how much time it is taken by the gate to change its state, that times are taken here. You can see in the diagram, it is written TPHL. That means when output changes from high to low, that time period from the input to output, how much time will take by the gate, that is considered here, and this time is for change in the output from high to low. So this is TPHL. At the second time, when input changes from high to low, output is changing from low to high, it will also take some time. Now this time is considered for only output. So when output changes from low to high, this will also take some time, and this time it is now considered as TPLH, low to high. Now average of these two time periods, it is called as propagation delay time. So in this way, the propagation delay time of any digital circuit or logic gate, it is calculated. So propagation delay time, in short, it is nothing but it is the time taken by the gate when the input changes from one state to other state. So how much time that gate will take to change its state at the output, so that delay, it is called as propagation delay. Now the next definition is power dissipation. Its unit is watt. You might have seen that in the household bulbs, they comes with the categories of various powers. That means 1 watt, 2 watt, 3 watt, 5 watt, so on. So this much value of power, it is utilized by the bulb, and so that much power is dissipated in that bulb. In the similar way, if digital ICs are used, this IC may dissipate the power. So this is the power dissipated in the IC. It is determined by the current that IC draws from the supply. So current multiplied by the voltage level, it will be the calculation of power dissipation. It is desired to have lower power dissipation because it reduces the cost of cooling and the cost of power supply. So power dissipation is the very important parameter or important characteristics in digital IC. Now the next thing is the figure of merit. You may know the meaning of merit. Merit means if the value is lower, that value will be the merit. So in the similar way, which ICs or which logic family is better, we have to calculate this, or to consider this, we have to calculate the figure of merit. This figure of merit in the IC, it is calculated as the product of speed of operation and the power dissipation. So if merit is there, the low value should be desirable. The figure of merit is nothing but multiplication of propagation delay time and the power dissipation in the IC. Its unit, or it is specified in the picojoules. So this was about figure of merit. Now next is the fan out, means it is the rating of number of similar gates which can be driven by the gate, and this high fan out it is desirable. The meaning of fan out is nothing but, suppose we have a gate and its output is logic 1, and suppose the output level is 5 volt. If similar gates are to be connected at the output of this gate, if one gate is connected, no problem, output for logic 1 will be 5 volt. But if the same output is connected to another gate, the voltage level at the output of this gate may drop. So it may become 4.5 volt for example. If another gate is connected, it may again drop by 0.5 volt, so it will become 4 volt. If another gate is connected, then voltage level will be 3.5 volt. And if the output is in the between 3.5 volt to 5 volt, it will be considered as logic 1. But if the fourth gate is connected, the output of this gate may drop again by 0.5 volt. So it will become now 3 volt. If 3 volt is there, then that voltage level will not consider as logic 1, because for logic level 1 at the output the voltage level should be 3.5 to 5 volt. So we can only connect 3 similar gates at the output of this gate. So 3 is the fan out in this case. So high fan out is desirable. In the similar way, fan in can be as defined. The fan in is the rating correspond to the number of inputs to the gate. So how much inputs can be connected to input of gate, that number is called as fan in. Now the next definition is the operating temperature ranges. In the digital field, there are many ICs which are used as logic family or logic gates. So this is the temperature range in which the IC will function properly. So that is the operating ranges. For consumer and industrial application, the operating temperature range is from 0 to 70 degrees Celsius. And for military purposes, it is minus 55 degrees Celsius to 125 degrees Celsius. You might have seen the prices of mobile phones. Some mobiles, they are available in the market and they will start ranges from 10,000 to up to maximum 50,000. But as you consider iPhones, the cost is very high, because semiconductor devices which are used in this type of phones, they comes in the operating temperature ranges from minus 55 degrees Celsius to 125 degrees Celsius. Obviously, the cost of the semiconductor devices may be high. This is the difference between the low cost phones and high cost phone. So operating temperature ranges are very important parameter or characteristics in digital ICs also. Now the last is the power supply requirement. We have seen two type of logic families, that is TTL logic family and CMOS logic families. The power supply requirement for TTL is plus 5 volt and power supply should be regulated power supply. While for CMOS, this voltage of power supply requirement, we can use a power supply from 3 volt to 15 volt for CMOS gates. So this was all about the characteristics or parameters of logic ICs. As we have studied TTL and CMOS logic families, we have to compare these logic families to understand which logic family is better. We have to compare the parameters of TTL gate and CMOS logic families. Let's have a look at the table for comparison of TTL and CMOS logic family. Number 1 is the circuit. In TTL, it uses transistor. So output of one transistor is connected to the input of second transistor. So the basic circuit is the transistor circuit in case of TTL. And in CMOS, it uses MOSFETs, P-type and N-MOSFETs, and these MOSFETs are connected in complementary connection. So the basic circuit is complementary MOSFETs in CMOS. Second parameter is basic logic function. TTL gate, it uses a NAND gate as a basic logic function to construct remaining gates, while in CMOS, inverter is a basic function which is used to construct remaining gates. Third comparison is wired collector capability. TTL gate, it is collected with passive pull-up. Now passive pull-up means at the output we have to connect a resistor. So the resistor and LED is the passive device. Our output is taken with the help of resistor. So with passive pull-up, the wire collector capability of TTL can be obtained. While in the case of CMOS, the output is always connected with the tri-state output. Now the fourth is the noise immunity. In TTL, the noise immunity is good, but while in case of the CMOS, noise immunity is very good to excellent. That means CMOS gate has good or very excellent noise immunity. So it can withstand with stray electric field or magnetic fields very faithfully. So excellent noise immunity in CMOS. For TTL, the power supply requirement is 5 volt, while in case of CMOS, it is from 3 volt to 15 volt. So we can use any voltage between this range from 3 volt to 15 volt. In TTL gate, noise margin is very high, while in case of CMOS, noise margin is very low. The seventh point is the propagation delay. In TTL gate, the propagation delay is only 10 nanosecond, while in CMOS it is 50 nanoseconds. That means TTL is better in case of propagation delay time. Then 8th point is the compatibility with other families. TTL gates can be compatible with DTL only, and CMOS are compatible with TTL if the power supply in CMOS logic family or logic gates, it is only with 5 volt power supply. If 5 volt power supply is used in CMOS, then it is compatible with the TTL. That means TTL and CMOS can be connected to each other if the power supply in CMOS gate is 5 volt is used. So this was all about the comparison. So for this we have studied the characteristics or parameters of the TTL or CMOS logic families. So these parameters are used to compare the logic families, which logic family is used for better operation. Along with this, there are certain advantages of CMOS. That first advantage is the quiescent and static power dissipation is very small in case of CMOS, and it is almost a few nanoseconds, few nanowatt only. The noise immunity of CMOS is very good. The propagation delay time is about 50 nanoseconds, and fan out may exceed up to 50. See the value of fan out. That means 50 number of gates can be connected at the output. So high fan out is there in case of CMOS. Then in CMOS, a single power supply is needed. If power supply's voltage is 5 volt, then CMOS and TTL gates can be interconnected. Then in CMOS, the temperature stability is very good. So these are the advantages of CMOS. So that is why we are using CMOS devices in digital field. So this was the advantages of CMOS. In the next topic, we will discuss on the tri-state logic. What is meant by tri-state logic, or how it is constructed, how it is used. We will discuss it on the next topic. Right now,